we have Fausto Carcassi and Giorgio Sbardolini talking about updates and Boolean universals.
Thank you, Julian, and thank you everyone else for coming here. I hope you can see my slide. I think that should be all right. And I shared also the slides in the chat for those of you who want to look at them. So in this paper, we are going to talk about one aspect of semantic universals. So this regularities that seem to hold across natural languages about semantics. A famous one, for example, is the fact that quantifiers in natural language are monotonic. We're talking about lexical gaps. In other words, the fact that the lexicon of natural languages, in the lexicon of natural languages, there are certain kinds of operators that don't appear, and that's in a way surprising. Let's see what I'm talking about. Natural languages, as we all know, include Boolean operators, conjunction, disjunction, things like this. These operators are functions from truth values, the true and the false, to a truth value, at the very least. Like that's the simplest semantic analysis you can give. And languages across the world seem to be divided more or less in these families or in these categories. There are languages like English that contain and, or, and nor. So the nor is the negation of disjunction. There are languages that contain only conjunction and disjunction, languages that only contain one of those. So this is a very short overview of the typological evidence. There are some certain striking facts about this data. In particular, a lot of the literature is focused on the absence of NAND. NAND would be negated conjunction, so that if you say something like P NAND Q, that should be true just in case it's not the case that P or it's not the case that Q. Now, why would NAND be missing when you have and, or, and nor? If you think about it from an Aristotelian square perspective, 3 of the 4 squares are occupied. Why is the 4th missing? So from a certain strictly, say, semantic or logical perspective, these kind of gaps are unexpected if the representation, semantic representation of these words, and, or, and, or, for example, are just intersection, union, and complement. Because once you have those in your language of thought, so to speak, then there's nothing apparently that prevents you from having a way of defining, a very straightforward way of defining NAND. Our goal is to explain the patterns of lexicalization we observe in natural language. And the plan is to do this in a version of update semantics. So we saw, we had an introduction to update semantics, or a reminder about update semantics yesterday in Manfred's talk. The main idea is this: the utterance of a sentence updates the context, and different Boolean operators correspond to different updates procedures, not all equivalent in terms of complexity. And so, well, it's going to turn out that the operators that exist and the way they are distributed are those that minimize a couple of measures of complexity that we're going to define. So now you might be wondering, what the hell are these people doing in a workshop on speech acts other than assertion? And the answer is the update we use is bilateral, and it's work that I've also been doing, in which Luca is also involved. So really, this is perhaps like a 3 brains project at the moment. The crucial idea is that sentences can be asserted. The idea that you need an update system to calculate how the assertion of a sentence modifies the context, that goes back to Stolnaker. Lots of people have worked on it. But we also make it a primitive that sentences can be rejected. You'll see in a minute why this idea pays off in terms of the explanatory work we want to do. So this is the outline of the presentation. I'll do some problem setting. At the beginning, I will give a brief introduction to the bilateral update system. We'll discuss the easy cases. So we'll discuss conjunction, disjunction, and negation. And then we go back to the problem with NAND. we will show that, or as we will discuss, the way to include or encode NAND in the update system will require us to add some layer of complexity. And this, again, is crucial to our explanation. And once I've introduced that key point, then Fausto will take over. Okay, so problem setting. As I mentioned, languages seem to fall in different families. So again, there are languages that contain conjunction, disjunction, nor, and so forth. To these languages, to these operators, we also add negation, because negation is also universally lexicalized. But that seems to be that seems to complete the overview of what Booleans exist in nature, so to speak. Now, the problem is much richer than why just there is no NAND. This has been noted. And in particular, there are also, in total, there are 16 binary Boolean operators that are definable over the two truth values. We only see 3 of them. So we don't see NAND. We also don't see the biconditional. We don't see all of the other combinations that can only be expressed compositionally. So the way to express NAND in English, for example, is to say not both A and B, right? So not just that, it's also, there's also the problem that must be explained. It is also why, for example, nor does not occur alone. Why, in other words, the operators that do exist come around in the combinations that they do. Okay, so now I will simplify the problem a little bit, make some assumptions for simplicity. We focus on binary uses of the connectives. We focus on propositional uses, so the arguments of these operators are going to be propositions. Okay, so the key point to explain is why these functions occur in the lexicon. And so the crucial notion is lexical simplicity. It's not, so what that means, we take it to mean monomorphonicity. So there being a single morpheme in the language that expresses that function. This follows Keenan Studies approach. I mentioned this because you might be aware that there's a debate on whether English nor and analogous expressions in at least in Germanic languages are syntactically simple. I'm not going to get into this debate. But that's a stipulation we make about what it means to be a simple lexical entry. Now, we are aware that there is an explanation of these facts that goes back to Larry Horn. It's a pragmatic Graysian explanation. It's been revised recently by Katsir and Singh, by Wagaki. And we will get to that, a brief comparison between our approach and this, broadly speaking, Graysian approach in the conclusion, if there is time in particular. And final point, final assumption to set up the problem, we're assuming that these Boolean here have the static interpretation that you expect them to do. So conjunction is intersection and disjunction is union and so forth. Right, so now, introduction to bilateral update semantics. The idea that, okay, so there's this general approach. This is generally a sentences carry information that modifies the context in which they're uttered. This idea has been crucial for the study of a variety of phenomena, primarily things that have to do with the interpretation of epistemic models and of anaphora. We're not really interested in those dynamic aspects of language. Okay. So in fact, the language that we will be interpreting does not contain any dynamic component like the epistemic modality for Feldman or anaphora. Now we move one step beyond. Conceptually, one step beyond the traditional update systems, and this is in work that, as I mentioned, I have done with Luca. we say that sentences can be asserted, but they can also be rejected. So we need a way to calculate how information is added to a context and also how it's removed from a context. Thus, we distinguish two kinds of updates, positive and negative. What is the plus or minus? So the plus or minus are force signs. They indicate the force of an utterance. The force can be assertion or rejection or denial. What force does, it will, as I will show by example in a minute, force contributes a change in the order of possible words. We assume that possible words in the context are ranked according to how likely it is that each word is the actual word. Imagine this in a very Stalnackerian setting where the interlocutors are trying to figure out which word is actual, and they attach to each word. For each word, they have an assessment of this or the plausibility that it's actual. So what happens is, if P is accepted, the word in P, so the word in the semantic content of P, are ranked higher. They go up in plausibility. If it's rejected, they go down in plausibility. They're ranked lower. We are in this way of thinking about the dynamics of the common ground. I'm assuming that everything is cooperative. There's no agents are informed, and all of the simplifications of the case here to keep things manageable. Furthermore, the updated, once you have rearranged the possibilities according to likelihood, the updated context is defined by restriction, such that only the highest ranking words are kept. So the updated context is the set of words in the input context that are ranked highest given the utterance. Let's see how this works by example. Consider a very simple context that contains just 4 possible words. So this is going to be a way of representing a truth table, basically. So you have I hope you can see my cursor. You have W1 here, which is such that P is true and Q is true. Then W2, P is true, but Q is not, and so forth. At the beginning, all words are ranked at the same level, right? So the interlocutors find all of these words equally plausible as a candidate for the actual word. Then what happens? Suppose that P is asserted and accepted. So now we are decomposing, in effect, the notion of an update into 2 parts. The first element is that the P words get ranked higher. So the P words are W1 and W2, right? And these get ranked higher. I'm representing this in the picture on the right by this color orange. Next, the new context is defined by keeping only the highest ranking word. So this is, as you can see, as a result, we get that C plus P is just the intersection of C with the static meaning of P. Here P is an atomic sentence. So in effect, things work out as in the Stalnackerian approach, Veltman's approach. The difference being that in Stalnacker, you only have the restriction, right? And we also use this rearrangement of words. Why do we do that? Well, because we want to deal with rejection directly. So if P is rejected instead, then in the same context, the ranking becomes one where the P word drop down. So which I'm coloring in this blue here. And then the new context is defined by keeping only the highest ranking word, saving only them, right? So the gray area gets dropped, and the new context will contain W3 and W4, which is, of course, the complement of P. So this is important because we're going to use this kind of structural correspondence between certain kinds of update, certain kinds of formulas in the language of updates, with the possibility of intersecting the common ground with the static meaning of a sentence to say that, in this case, for example, C minus P, so rejection of P, characterizes negation of P, or we can say that rejection encodes negation. I'm gonna use this phrase as well. Okay, question so far?
So are those updates order independent?
Order independent.
So no matter, I mean, let's say you have a bunch of propositions, and no matter how you apply them, then you will get the same results. I mean, in what order you apply them, you'll get the same result.
Yes. I'm not sure I have quite such a strong proof yet, but I think yes.
Right.
Okay, well, maybe things will also be clearer as we go along. Maybe I should also say that this is very much, a lot of it is work in progress, but yeah, they are to some extent, yes, I think they should be order independent. Also, in particular, this depends on the fact that there are no, in the language we have been using, there are no operators like, there are no tests, right? So there's nothing like dynamic might, which would disrupt that, order independence. Okay, now let's move on to the easy cases. So the next step we have to do is we have to discuss how context is updated with the information that comes from more than one sentence. And this can happen in order or not. So just to get an idea of what I mean, it will turn out that ordered positive updates with P and then with Q, those correspond to conjunction. So this is the way to encode conjunction. Here's an illustration. The series of pictures really represents the procedure, the algorithm that correspond to the computation of conjunction. So we start with our initial possible word, initial context of 4 words. Then P is accepted, so it's colored, the proposition P gets colored orange. The highest ranking word are kept. So at this point, an intermediate context is defined. And in this local context, the Q word are accepted. This is only W1 in this case. And the rest is dropped. So as a result, we end up with intersection. As you can see, this is Heim's dynamic account of conjunction. Yeah. So exactly. So this ordered positive updates with P and then with Q is the way to encode and. Order, just to fix ideas, is a matter of generating an intermediate context after the first sentence is accepted. This step of generating an intermediate context is not necessary. In fact, we can also provide an update with P and then with Q, a positive update with P and then with Q, by doing things not in order. So without the intermediate context. So if we do that, then we start with our context. We push the P words high up. Then we push the Q words up. At this point, we have accepted everything except W4. And then we perform the restriction by keeping only the highest ranking word. At this point, you see that the result characterizes this junction. Okay, and yeah, the difference is simply that no intermediate context is defined. Now, this is the basic, and let's go back to talk about NAND. We have seen 2 basic ways to add information of the information of multiple sentences. It can be in order or it can be not in order. The first option characterizes conjunction, the second disjunction. How about removing information now? Okay, so if we do things in order, this is what we get. You start from the initial context, you drop the P words, define an intermediate context. This is now going to be the complement of P. Then drop the Q words, and your final context will be the complement of disjunction. Right? If we do things not in order, starting from the same point, drop the P words, drop the Q words, define your context by keeping only the highest ranking one, you get to the same result. So this is, interesting because the simplest way of defining negative updates, given the framework that we use to define conjunction and disjunction, and the simplest way is just to flip the plus into minuses, collapse into NOR, into a context in which neither P nor Q is true. So NAND is missing from this, and so are the remaining booleans. Okay, so then the next thing that I will add is that if we want to encode these additional operators, we'll have to go one step higher. We have to add more structure. We'll have to add more complexity, and this is key to our explanation. The thing in particular that I will introduce are global updates. So far, we've only considered formulas in updates.
I don't understand what you mean by saying NAND is missing, and I want to follow. Can you just give me another clue by that? Sorry, Giorgio.
Yeah. No, okay. No, it's important to be clear here. So I'm presenting this update system, building it up from the basics, right? So far I give you the way to start with updates of single sentences and combine them to characterize conjunction and to characterize disjunction, right? And then the idea is now we have to find a way to encode also, well, the remaining Boolean functions, starting from NOR and then NAND and then the rest, right? So if you take the architecture needed for conjunction, which is just a sequence of updates, positive updates, and you just flip them into negatives, you get this procedure here on top, which characterizes NOR. If you take the architecture for disjunction and you flip those as assertions into rejections, you get the same. You get at the same point. So it's no progress. So using only the conceptual primitives that I introduced so far, what we get our conjunction is a sequence of positive updates. Disjunction is a not ordered, an unordered sequence of positive updates, and NOR, it's well, there's no distinction here. Because yeah, there's no distinction. Order or not order doesn't matter for rejections, for multiple rejections. I hope that clarifies.
That's very helpful. I appreciate that. Thank you.
Good, you're welcome. So then, exactly, as I was saying, we need an extra step to encode the remaining Boolean functions. The one I will introduce, which is crucial, is the idea of global updates. It goes like this. So at this point, we have only considered formulas in the update system in which the context appears as input only once. You can think of these formulas as describing local updates. So in other words, you give an input C, and then those formulas describe an update procedure that unfolds by progressively restricting the initial C. So they're only local, right? You only have to look at the context once at the beginning, and then you work on it. Yeah, but the language of updates might allow update procedures to be more complex than this. So here's an example to get a sense of what I mean. Consider this formula here. So here we have embedded a positive update with P inside a negative update, a larger negative update. Here's what procedure this formula describes. Starting from inside out, first there's a positive update with P. It gets you to a local, to an intermediate context, C plus P. And at that point, you can recall, so to speak, the initial input, C, and perform a negative update with the result of the first update. So intuitively, this is equivalent to rejecting P in C, but now the crucial difference is that C appears twice. Here's an illustration of this process. So you start from your context. The first thing you do is C plus P, right? So you accept the P words and then you drop the rest. And then the information that you collected here, you're gonna reject it from the initial context, right? Which gets used again. and then define the final context. So that should give you a sense of, and really, as I mentioned, in this specific case, it's just equivalent to rejecting P from C once. But the idea that the context input can be used more than once is very powerful. Why? Well, for example, it gives us a very straightforward way of introducing NAND as a global operation. It's just like this, right? So you start from, again, from
Giorgio?
Yes.
I think Krivka wanted to say something.
Just one point. This formula of negation was actually the one that Irina Heim proposed in her paper on presupposition projection. And this explains why presuppositions are kept under negation. So she has a formula for negation in her 83 paper that is exactly that here. But
so in the 83 paper, okay, what is the formula for negation that she has?
C updated with, it is not the case that P is C minus C updated with P.
I see.
And she explains the projection behavior of negation.
But minus is the set theoretic complement, right?
Complement.
Yeah.
Yes. Yeah, that's interesting. Yeah, well, of course, the crucial difference is Heim assumes that, or at least, yeah, Heim assumes that the Heim doesn't have a negative update as a primitive.
Exactly. She just has subtraction of one context set from another one. This she has is
yes. I suppose that in that framework,
and she cannot have negative updates because she works with discourse reference in addition, and she would have to define negation or and discourse reference. You can only increase, you cannot decrease the set of discourse reference. Yeah, I think this is her basic motivation for that.
Okay, I'm gonna have to think about that. It's definitely an interesting challenge to think about how this well, I mean, the task here is not to account for presupposition projection, but for sure it would be nice to figure out how this works out with presupposition projection. So I'm gonna have to think about that. Thank you. As I mentioned earlier, in response to Jakob, yeah, there's nothing in the language here that projects anything. I mean, at least, you know, simplifying things a little bit, perhaps. Okay, that would, yeah, as I said, that would be an interesting challenge. Now, back to global updates. With the possibility of iterating the input C, NAND can be expressed. It's expressed by, first you calculate conjunction, right? So you calculate C plus P then plus Q, and then you take it out of the initial input. So in fact, this is the complement of conjunction. And yeah, Manfred's observation is exactly right, because this possibility of doing global updates, global negative updates, is the way to characterize complement fully, which we didn't have with simple rejections, which is the reason why we don't have NAND in the simplest possible way of writing updates. Okay, however, global operations of this kind do seem more complex. The input must be processed more than once, in particular. So this is a representation of how NAND works out. So first you calculate your conjunction, and then you use this, you zoom in on this information set that you have arrived at, and you take it, and you push the words in this information set down in the ranking of the initial set, on the initial context. That gives you NAND. I hope this was clear. And the next thing we're going to do, but Fausto will take over, is to explain that natural languages lexicalize Boolean operators by minimizing the complexity of the update procedure that characterizes them in the language we have developed. I conclude by showing you this table, which represents, so here you have the 16 booleans of binary booleans with their truth table and the shortest formula in the notation we've developed that characterizes the truth conditions of the formula. There's a horizontal line here at some point, because this is because the operators below the line are trivial in some sense, right? So they're not particularly interesting. So I think Fausto will skip part of in his discussion. We skip mentioning these, although they are included in the simulations later. Okay, this is what I wanted to tell you. Now I'll give the word to Fausto.
Hello, everybody. Let me see if I can share my screen.
Fausto, do you have slides you could share?
Oh, yeah. Give me a second. So chat. Oh, yeah. So I hope that reached everybody. Okay, I'm gonna share my screen again. All right, so there isn't a lot of time, so I'll have to do a bit of a short squeeze of the rest of the talk. Okay, so let me see. Okay, so sorry, I have to move a bunch of screens. Okay, so can everybody see my screen? The PowerPoint? Yeah, okay, good. Okay, so here's the structure of what I'm going to talk about. First, I'll define a measure of conceptual complexity based on the language that Giorgio talked about. Then I say a little bit about evolution of language as a response to two pressures. One of them is going to be one pressure for complexity that I'm going to define in the first part. So first of all, a measure of conceptual complexity. So the claim here is that the updates described by Giorgio, so the ones in the final table, are some kind of language of thought in which we encode the Boolean connectives in the natural language. So we can then expect the conceptual complexity of each Boolean operator to be a function of the complexity of the update. And the question then, of course, is what features of the update contribute to the conceptual complexity. So one very natural way would be to just have the length of the update formula, but that depends on kind of arbitrary syntactic choices that we don't want to kind of include in a natural measure of complexity. So it seems more plausible that some other features of the updates, like globality, will have a role in determining complexity. So we propose that three features are relevant here: globality, polarity, and homogeneity, and I'm going to take them in turn. So first of all, globality, and it encodes whether, as Giorgio said, whether the global context C appears more than once in the update. And the claim is that global is cognitively more costly than local. So as Giorgio already mentioned, globality implies that the agent cannot simply forget the initial global context after each update, but rather they need to remember it because they need to use it later on. So for instance, in this update of simply and, the agent, once they define C prime in at point 2 in line 2, they can C never appears again. So they only need to remember the current state. But if the agent is calculating the NAND, then in line 2 in context C prime is defined, but then the original context C appears again in line 5. So it needs to keep track of it. So there's some I'm gonna just give some kind of impressionistic connections here. And there's one connection to the complexity of proportional quantifiers that require pushdown automata and so require memory as opposed to the simpler memoryless Aristotelian quantifiers. And Semantic is here, so maybe he has some more ideas about this connection, but we can come back later in the Q&A. So hopefully these connections become clearer once we extend this to quantifiers. So our definition of globality is binary. meaning that either an update is global or not, but it can be refined in various ways. So by the number of times C appears, or by the number of contexts the agent needs to keep track of at the same time, or other things that we can discuss in the Q&A. Okay, so second feature is polarity, and we define polarity simply as whether the update contains at least one rejection. And the claim is that having a rejection makes the formula cognitively harder. So for local updates, there is a simple connection between polarity and monotonicity. Acceptances correspond to upward monotonic, and rejection correspond to downward monotonic. So I'm going to skip the definition of monotonicity because you probably all know it. But you can see it in this table that, for instance, P and Q is upward monotonic in both arguments, and both of the arguments are accepted. And on the other hand, the negated conditional is upward monotonic in the first argument, which is accepted, and downward monotonic in the second argument, which is rejected in the corresponding update. So there's this kind of nice, neat connection between the two, at least in the local updates. In the global updates, where the context is rejected, the connection is switched. So the upward monotonic are correspond to rejections, and vice versa. Okay, so in the case of quantifiers, there is previous work showing that downward monotonic is cognitively more costly than upward monotonic. So Hertz and van der Slik have this 2005 paper. And that's again a possible connection, but still quite impressionistic. Okay, and finally, homogeneity encodes whether the update contains only rejections or only acceptances, or some mix of the two. And the claim is that heterogeneous is more costly than homogeneous. So translated into the monotonicity language, mixed monotonicity would be harder than homogeneous, so the same monotonicity for the two arguments. So given the connection that we discussed, again, there's this interesting connection to the results in Hertz and van der Slik, where they show that heterogeneous monotonicity is more complex than homogeneous monotonicity. Okay, so what follows from this definition of complexity? Well, P and Q, for instance, is local, it's homogeneous, and it is positive. So there's local because there's only one C, it's homogeneous because both of the arguments are accepted, and it's positive in the sense that there isn't any rejection. NOR is local, there's only one C, it's homogeneous, it's both rejections, but it's not positive, there's at least one rejection. And NAND is global, it's not homogeneous, and it's negative. Okay, and then you can kind of calculate the which of these complexity features each of the possible connective has, and you get kind of a rank of complexity for these connectives. So we rank the formulas with respect to the complexity by calculating how many of the features they have. And again, the absolute value of complexity doesn't really matter here, as long as the rank remains the same, for reasons that I'll come to in a second. So first part of this section, we have defined a measure of complexity for updates based on three features of the update themselves. The observed operators are among the simplest ones, in the sense that, I'll come back to this, in the sense that AND, OR, and NOR are the operators that have most of the features that make them simple. And the measure of conceptual complexity makes empirical predictions about the rank of complexity of the Boolean connectives. So this could be tested experimentally in future work. So are there any questions at this point? It's kind of already over time, so we can also just do it in the Q&A. Okay, I'll just keep going and then we can come back to it. So the order of complexity is, oh, there's something in the chat. Oh, I can see the chat.
So Leila is asking if the conditional would be more complex than its negation.
I see. Let's see. Yeah. So that follows from this definition of complexity. We can, so we can come back to that in the Q&A again. But that happens. So so next thing I'm going to talk about is how this kind of plays into a more general picture of language evolution. And we're going to talk about whole inventories of connected. So the order of complexity, so what I've talked about until now, is a good result, but it cannot be the whole story, because what we actually observe in language are inventories of operators. And plausibly, whether an operator appears in language is not independent of which other operators that particular language contains. So in other words, from an evolutionary point of view, selection happens on whole inventories of operators rather than individual operators. A very simple case of this would be functional completeness. So namely, whether an inventory can produce a possibly compositionally obtained sentence for every possible state. And for instance, and, not, or, not, and nor are complete, but and by itself and or by itself are not complete. So if we assume that natural languages are complete, then we need to consider the whole inventories. We can't just by knowing whether the language is and or not, know whether it satisfies this condition of functional completeness. So this was just an example. Okay, so we assume that the observed lexical inventories are a consequence of two opposing pressures. One hand, there's a pressure to keep the total complexity of the inventory as low as possible, and we calculate that just as is sum of the complexity of the connectives it contains. On the other hand, there's a pressure to have inventories that are in some sense easy to use. So next I'm gonna describe how we measure this in very simple terms. So imagine a speaker who observes one of the possible 16 states, and then they have to produce a signal to communicate the observed state to the listener. And they can compose operators. So we have a speaker and a listener, and they use this language that contains and not. And then the speaker observes a point. Let's say they observe P and not Q, and then they produce a sentence which uses the operators they have in the language to communicate the observation to the listener. In this case, they use P and not Q. And we measure user complexity as the average number of operators needed to perfectly convey the observation with whichever lexical inventory the agents are using. Okay, so this plot shows on one axis the conceptual complexity that we define based on the language of updates. And then on the other axis, the user complexity defined as the average number of operators needed to encode any kind of an observation with that inventory. We use all combinations of up to 5 substantial operators. That means operators that make use both of the arguments plus not, which we assume is lexicalized for independent reasons, and so we assume is part of every language. And each point here, it corresponds to one language or more languages because they can overlap with each other. Okay, so the attested inventories are in red, and what you see is that they are in the Pareto frontier. And what this means is that given a language in the Pareto frontier is such that given its level of conceptual complexity, it cannot get any better in terms of the user complexity, and given its level of user complexity, it cannot get any better in terms of the conceptual complexity. Okay, so let's look at what the individual languages are. And not is here. So the inventory containing just and not is here because it has very high user complexity. So you're going to have to use very nested expressions to express some of the observations. But it has low conceptual complexity because and not are both very cheap cognitively. Or and not overlaps with and or not because the level of nesting on average is the same, and or is as costly as and in our measure of complexity. Then and or and not is a bit better in terms of the user complexity. So you have to use less nested expressions to express observations, but it's a bit more costly because from a point of view of conceptual complexity because it contains both and nor. And finally, and, or, nor, not. Again, it's even better in terms of user complexity, but it's a bit worse in terms of conceptual complexity because you have even more operators. Okay, so we're out of time, so we can come back to this. This was a comparison to Wagaki's model, but since he's here, we can maybe he has more insightful things than I had on that slide. So in conclusion, we have developed our bilateral update semantics to encode the Boolean operators. In contrast to previous accounts, we assume 3 primitives: acceptance, rejection, and restriction. Argued for a measure of simplicity where the attested operators are the simplest ones, and then we have defined a measure of complexity in use for the whole inventories. And finally, we've shown that the attested inventories tend to be optimized for usage complexity on the one hand and for conceptual complexity on the other hand. So they are the ones that strike the best possible compromise between these two pressures. Okay, yeah, that's it. Thank you. Yeah, that was